Find a basis for the column space of this matrix A. To start with, I'm going to reduce this to its reduced row echelon form. Although, to make this work, we really only need it to be in row echelon form, but I happen to have it written in my notes in reduced row echelon form, so that's what I'm going to write. Here's the reduced row echelon form. Quick question. Is the column space of A equal to the column space of B? Think about that for a moment. Pause the video, and when you've decided on your answer, come back. Okay, now that you're back, the answer is no. Well, why not? It's because all the columns of B have 0 at the bottom, so you can't get any column of A using them. And when I say using them, I mean using linear combinations. More generally, the column space of A and the column space of its reduced row echelon form are not the same. On the other hand, AX equals 0 and BX equals 0 have the same solutions, which we already know, and therefore have the same dependency relations between their columns. So in other words, if a linear combination of the columns of A with a certain set of coefficients gives you 0, those same coefficients, when I make a linear combination of the columns of B, will give me 0 also, and vice versa. I'm going to use this fact to find a basis for the column space of A. To give myself a little bit more room, let me take all this stuff here and make it a lot smaller and put it over here. Next thing I want to do to make the talking about things a little bit easier, I don't want to keep referring to the columns by what's in them, so let's write the columns of A as A1 through A5, so let's call these A1 through A5, and B, let's call them B1 through B5. Now on to the actual computation of a basis. The first observation I want to notice, is that after doing a little bit of calculation using this reduced row echelon form B, the vector form of the solution set of, or I should say, I should say a vector form of the solution set of AX equals 0 is X equals S times 1, 2, minus 1, 0, 0, plus T t times minus 1, 3, 0, 4, minus 1. In particular, this means that a times the first vector over here times 1, 2, minus 1, 0, 0 is equal to 0, and a times the second vector here is also 0. And this implies, therefore, by looking at this and this as dependency relations between the columns as linear combinations of the columns which give us 0, this tells us, after rearranging terms, that A3 is equal to A1 plus 2A2, and A5 is equal to minus A1 plus 3A2 plus 4A4. In particular, A3 and A5 are redundant when it comes to computing the column space. So, in other words, the column space of A is the span of the vectors A1, A2, and A4. I want to emphasize, and we'll see this come back later, that this 1, this 2, and this 4 are exactly column indices where we have leading 1. So this is column 1, this is column 1, and this is column 1. So my claim is that they actually form a basis. A1, A2, A4 form a basis for the column space of A. All that's left to do, since we know that they span, is to show that they are linearly independent. How are we going to do that? Let's use B. In particular, we're going to use this fact here that B and A have the same dependency relations. Notice that if C1 A1 plus C2 A2 plus C3, or actually let's call it C4, just to emphasize, C4 A4 is equal to 0, then by what we talked about right here, the same is true for B1, B2, and B4. So C1 B1 plus C2 B2 plus C4 B4 is 0 also. But B1, B2, and B4 are linearly independent. So C1 equals C2 equals C4 equals 0. Therefore, by the definition of linearly independent, by definition of linearly independent, A1, A2, and A4 are linearly independent. Therefore, they form a basis. Since we already know they span. Boiling this example down to its essence, to its bare bones, we get the column method. Our given and our goal are the same as for the row method. We're given a subspace spanned by some vectors v1 through vk, and we want to find a basis for that span. Our first step is to form the matrix whose columns are our given vectors. So remember, in the row method, we formed the matrix whose rows were our given vectors. In the column method, we formed the matrix whose columns are our given vectors. Our second step is the same. We reduce A to its row echelon form. I used reduced row echelon form because it's easier to see things, but all we need is the row echelon form here, and let's call that row echelon form R. And finally, a basis for S is given by the columns of A corresponding to the leading entries of B. The most common mistake when using the column method is to use the columns of B instead of the columns of A. If you remember the question that I asked earlier, the column space of A is not equal in general to the column space of B, so you're probably going to get the wrong answer if you use the columns of B instead of the columns of A.